All right, so today's lesson is over section 2.3, which covers Pythagorean theorem and similar triangles. Very quick kind of overview of the two topics. So we'll do an example that involves similar triangles, and then I'll do an example that involves Pythagorean theorem. All right, example 1. In the figure shown, the isosceles triangle, so maybe from geometry class, isosceles triangle means two equal sides. Okay, so some definition there. So we know we're dealing with a triangle that has two equal sides. We're dealing with triangle ABC. Represents a cross section of a roof with a reinforcing strut DE. Okay, the base BC of the roof has a length of 20. So this entire length down here we'll label as a 20. The slant portion of the roof AD has a length of 10. And the slant portion of the roof DB has a length of 4 feet. Okay, so it told us an isosceles triangle, so our two sides are going to be equal here. I don't know if that really comes into a play with one of our questions. So question A says, find the length of the strut DE in feet. Round our answer to the nearest tenth of a foot. So we need to find this guy going across right there. Okay, so one thing that might help you out is, we should be able to see two big triangles hanging out in here, right? We've got one big triangle, but we also have a smaller triangle kind of hidden inside that. So what I'm going to do is I'm going to go ahead and separate those guys out so we can see the two triangles side by side instead of inside. Okay, so we've got a bigger triangle here that is labeled ABC. And length AB, well, he told us one side or one part of it is 10, the other part is 4. So this side is 14. This length BC down here is a 20. And again, with it being an isosceles triangle, I don't think it really doesn't matter, but we'll just call it the 14. So we'll say those two sides are the equal sides. And then I will pull out the smaller of the triangles. So I'll draw a little smaller. And the smaller triangle is ADE. And remember, it is this length here that we really need to come up with, right? That was question A here, length of DE, okay? Well, again, AD, they told us it had a length of 10. Again, it doesn't matter what that length is because we need this guy. That was the more important part here. So now we have similar triangles, right? They have all three angles are the same. So we can we will deem these as a similar triangle. Remember, with similar triangles, they have to have a common rate between the two numbers, meaning so the rate between 14 and 20 needs to have the same exact number or multiplier, however you want to think of it, between 10 and this number. Okay, for these guys to be similar, the connection between side to side has to be the same number. Okay, so let's get into actual computing here. Let me grab a color. I'll grab this. All right, so one thing to kind of help us out to kind of keep our units in line here, I'm going to say let's compare the big guy to the small. So we're going to compare this blue triangle to the green triangle. Well, this side here, AB, is the same side as this. So that side for the big is a 14, but for the 10, or for the small is a 10 here. Well, that ratio has to be the same, right? When similar triangles, the ratio has to be the same. Well, this bottom guy is a 20 for the big triangle, and the bottom part of the triangle for the smaller guy, we're going to let it be an X. Okay, so here's your proportion, right? Anytime you're dealing with similar triangles, you're going to be dealing with a proportion. Here is the setup. Again, that relationship between the 14 to the 20 has to be the same thing, going from 10 to the X. Or mathematically, what we can really do is the way we solve proportions is through cross multiplication. So 10 times 20 is 200 is equal to the 14 times X. Okay, and then we're going to quickly solve here. That's multiplication. We'll undo that by division. And using our calculator, we can see that 200 over 14 is x is approximately, so remember I told us nearest tenth of a foot, so only one decimal place, 14.28, but we'll round that 2 because of the 8 on the second part to a 3. So it looks like that this length here, DE, should be 14.3 feet. All right, part B. Part B says find the height or the length of the line segment AF. Okay, so it's wanting us to deal with this. And we can assume that AF is an angle bisector. So it literally splits this guy in half. We can assume that this makes a right angle. It's a line segment AF of the roof in feet. So we want to round our answer to the nearest foot. So we need to find the height of this guy. And again, we can assume that this is an angle bisector, so it splits this in half, that whole thing is 20. We can assume that, you know, both sides are going to be a 10. All right, so again, our job here is to find the height. If it told us the area of this triangle, we could actually use the area formula to be able to kind of find the height here. It does not give us any indication of area, so the only thing that we can do here is pull out one of these triangles. So you should notice that I have a triangle kind of hanging out to the left, and I have a triangle hanging out to the right. It doesn't matter, it's the same thing on both sides. It's an isosceles triangle. So let's just go ahead and pull that triangle out to the left. So again, I really think it will help you if you redraw the triangle that you're dealing with instead of, you know, dealing with it with the whole thing in mind there. So what this is, now I have triangle AFB. Okay, and from our labeling before, right, this was the angle bisector part, so we just let that be the 10. And from the beginning, the 10 and the 4, we were able to say that entire length is the 14. Remember, our goal was to find the height of this triangle, which is now this part right here. We don't know what it is, so we're just going to call it X. Okay, so again, with the angle bisector, we know that this is a right angle or a right triangle. With right triangles, now we can apply the Pythagorean theorem. Remember, the Pythagorean theorem formula is a squared plus b squared is equal to c squared. And c squared is always the hypotenuse. This guy here is always the hypotenuse. And remember, the hypotenuse is always the side opposite of the right angle. So if my right angle is here, right, this 14 is going to be the hypotenuse. It's going to be the largest side. Okay, it doesn't matter which one we call A or B here, take your pick. So what we've got here is now we have 10 squared plus, right, we don't know this side, so we're just going to leave it as a b squared, is equal to, now the hypotenuse, right, the side opposite our right angle is 14 squared. And we're just going to simplify and solve for b. So 10 squared is 100. Again, we don't know what b squared is. We'll just leave it at that. 14 squared is 196. If I subtract the 100 over, now I'm left with b squared is equal to a 96. So now I have a square. We undo a square by square rooting. So I'm going to square root both sides of my equation there. The square root of b squared takes it to a b. That's why we do it. And then in our calculator, we're just going to hit the square root of a 96. Which gives us this repeating decimal, 9.7979, blah, 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 blah. It only wants our answer to the nearest tenth of a foot, so it wants us to round one spot. So if we have a 9.79, that 9 would round to a 7 to an 8. So we can say that side B here has a length of 9.8 tenth of a foot, so feet. Okay, so that example actually had both A had your similar triangle, and then B, we had to deal with Pythagorean theorem. Okay, one more example, example 2 of this section. Looks like this. All right, here we go. An observer spots a cyclist 50 feet north of him going east at 18 feet per second as shown in the diagram. Okay, how far apart is the observer and the cyclist 5 seconds after the observer spots the cyclist? Okay, so we've got an observer. They said it went 50 feet north, but then traveled at 18 feet per second, headed east. How far apart, right? That's this guy here. They labeled as D. How far apart is the cyclist after 5 seconds? Okay, so we want to know what's going on after 5 seconds. Well, that's key because, well, the cyclist was traveling 18 feet per second. So from here to here, right, from when they started heading east, if they went 18 feet per second for 5 seconds, we're going to say 18 times 5, which is 90. So we can say in the 5 seconds that this cyclist covered a distance of 90 feet. Again, we have a right angle involved here, so we can use our Pythagorean theorem. Again, just kind of filling in the blanks. Pythagorean theorem is a squared plus b squared is equal to c squared. Fill in what you know to solve for what you don't. So again, it doesn't matter what you label the legs. If one's A or B, it really doesn't matter. So let's just go ahead and fill this in. So this will say 50 squared plus 90 squared is equal to the side C, remember, is your hypotenuse, which is opposite the right angle. We don't know what side C is, so we'll leave it at C. 50 squared is 2,500 plus 90 squared, which is 8,100, is equal to C squared. We'll go ahead and add those two numbers up, which is 10600. Sorry. Is equal to the C squared. Again, we undo a square by square rooting, so I'm going to square root both sides. When we square root a square, we're just left with the what's underneath the house there. And then the square root of 10600, it wants us to round our answer to the nearest foot. So it doesn't want any decimals. Well, if I put in the square root of 10600, it tells us the 102.956, blah, 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 blah. It doesn't matter. It wants the nearest foot. So we're only going to look one decimal place, and it's a 9. So it's going to round that 2 up into a 3. So C is approximately 103 feet. Okay, so by 50 feet north, 90 feet east, that is going to give us an actual kind of cutoff distance of 103 feet. All right, so the remaining problems that I have assigned for this section followed pretty close to these two examples. There's a little bit more kind of investigating involved, but kind of the premise are still just the similar triangles that we talked about with example 1. Again, I really think it helps you, go ahead and separate those triangles out. If it's one just, a more specific triangle, don't look at it as a whole. And then, we've got our Pythagorean theorem there. Okay, reach out if you have any questions.